This lecture continues wave kinematics. It's specific to Physics AB and Honors Physics AB. What we want to do in this lecture is begin to understand how a simple periodic wave evolves or propagates with time. So then therefore at the end of the last lecture, here's where we were. We were taking a look at, for example, what a simple periodic wave looks like at a specific moment in time. That is when t is equal to 0, when we start the clock, and then here's the description that we have thus far. Okay, so what we do first of all is we plot here the direction of propagation, once again as the x direction, and then the displacement from the equilibrium position is the y-axis. And then at times t is equal to 0, we just trace out a cosine curve, if you recall, that looks like this. Okay, customarily here we always begin by just drawing a single wavelength, so the distance from crest to crest like so is lambda here along the x-axis, and then here and here are the amplitude positions, the maximum displacement from the equilibrium position. When time t is equal to 0, the function that we have thus far is this expression here. Okay, recall what the coefficient k refers to. It's the wave number. The coefficient k is 2 pi divided by the wavelength lambda. Now I'm beginning to describe the evolution or propagation of this wave with respect to time. However, notice that this expression here, technically speaking, is only a function of one variable. It's only a function of x. So now what we want to do is take this wave, for example, let's say that it's propagating to the right-hand side with some speed v, and then describe how this wave propagates with time. So let's say that some time t goes by. Okay, so t elapses. And then let's say that after time t, this green cosine curve that I've started with has propagated to the right-hand side some distance, that is like so. Okay, so once again, here's y and x, and then let me draw out the waveform, as we say, like this. And then the original green cosine curve that I started with, you'll notice has now propagated on the diagram. It is now propagated to this position here. Notice that this corresponds to a phase shift. So what we'll be using mathematically are phase shifts, as you'll see, to mathematically describe the propagation of this wave. Okay, now how far to the right-hand side has the wave propagated in time t? Well, if it has some speed v, that means that on this diagram, this distance here that the green wave has propagated to the right-hand side is this distance of vt. We now have to take this into account in terms of a variable. So then therefore what we do is we go into this function here and we replace the variable x now with a variable that includes this additional distance. That is like so, x plus or minus that distance of vt. As we'll see in some examples later on, it's a minus sign if the wave is propagating to the right. It's a plus sign if the wave is propagating to the left. But for now, what we need to come up with is a new function. So the way that we come up with that function is to go into this function here and then replace the variable x with this new variable that takes into account the additional distance here that the wave has propagated. That then gives us the following. Okay, so now let's go ahead and find this function, like so, which, as we'll see, will be a function of both x and t. So the way that we find this function is just go here to the original variable of x and then replace it with x plus or minus vt such that it looks like this. Okay, for now I'll put it in brackets here, like so, to describe the argument of the cosine function. But notice what I have done here, I've replaced the variable x with this now, x plus or minus vt. Okay, let's take a look at the argument here of the cosine function a little bit more carefully, that is off to the side. Okay, let's go ahead and distribute the k through the terms, and then when I do, I obtain this, and then right here is similarly to what we had before, just k times x. But then I also have here this new term of kvt. As we'll see, we've actually seen that before. Here's where we've seen it before. Okay, first of all, let me once again write the kx and now plus or minus the following. The wave number k is 2 pi divided by lambda. The speed of the wave is equal to the wavelength lambda divided by the period, and then here's time t. Notice that the lambdas cancel out here like so, and then what we have is 2 pi divided by the period, capital T. which we recognize from uniform circular motion and simple harmonic motion as the angular frequency omega. So then therefore the argument of the cosine function looks like this, where yes, the omega there is the angular frequency of simple harmonic motion. It describes the angular frequency of all of the simple harmonic oscillators that are in simple harmonic motion as a simple periodic wave propagates through a medium. Therefore, we end up with the following function as the kinematics equation that describes the propagation of a simple periodic wave. That is this expression here. Like so. Then, as we'll see with a numerical example in just a few moments, the way this function works is as follows. As time goes on, this number here, omega t, is continuously changing. And at an instant in time, that number, omega t, acts as a phase shift. And then, as we'll see with an example in just a few moments, as the wave then evolves with time, this then results in the propagation of a simple periodic curve in one direction or the other on the diagram. The easiest way to illustrate all of this, of course, is just with a basic example. So now let me go ahead and erase the board here, and then let's take a look at a detailed example. Okay, so let's go ahead and access the example. As is always the case, please copy it into your notes. Okay, a wave function is given by the following expression. Oh, let me neaten this up a little bit. There we go, like so. Okay, so 4 cosine of then the following. Pi over 4 times x, and then minus pi over 2 times t, all in terms of meters. Okay, in part A of the problem, we basically have to identify everything first. It says find the wavelength, frequency, period, and speed of the simple periodic wave. All of that information is contained here within the function. Okay, so first of all, let's just write down the amplitude. The amplitude is the coefficient 4 here in front of the cosine. And now in order to find the wavelength, we have to first of all identify the wave number k. So the wave number k is pi over 4 radians per meter. Okay, from there we can calculate the wavelength lambda, which is 2 pi divided by k. So 2 pi divided by 4, or pi over 4 rather, equals 8 meters. Okay, and then we have right here omega, the coefficient in front of time t. Omega is pi over 2 radians per second. And then from there we can calculate the period, capital T, which is 2 pi over omega. So 2 pi divided by pi over 2 is 4 seconds. And then from there we can find the frequency. It's just the inverse of the period, so that's 1/4 hertz. And then we can also find the speed of the wave at v, which is equal to wavelength times frequency. The wavelength here is 8 meters, and then multiplied by the frequency of 1/4 hertz, this ends up being 2 meters per second. So all of this basic information here about the kinematics of this wave is contained within the wave function itself. Okay, and now we're going to get to the graphing process here in part B of the problem. Let me move my file. Okay, so now in part B of the problem it says, show how the wave propagates for quarter period increments of time for one full period. So what I'm going to construct here are actually 5 graphs. Each of the graphs will be separated in time by 1/4 of a period. And then, as we'll see, this then results in a simple mathematical pattern that describes how the wave propagates with time. Okay, now of the numbers that I've calculated here, the numbers that we really need are the amplitude, the wavelength, and the period. Everything else is not necessary for this graphing process. So let me go ahead and keep those numbers here, like so. And now let's go ahead and start the graphing process by first of all describing what happens at times t is equal to 0. Okay, so at times t is equal to 0, all that we simply do is go into the function and set the time t equal to 0. That is like so. And then therefore, when the time t is equal to 0, we just simply start off with a cosine curve. So let's go ahead and graph that here. So here's x in terms of meters, here's y in terms of meters, and then starting off with a simple cosine curve here in green, that is like so. And then we always start off by graphing one full wavelength as I've done. So this distance right here is 8 meters along the x-axis, and then here and here the amplitude positions of 4 and -4 respectively. And now let's see what happens after 1/4 of the period has gone by. As we'll see, the minus sign here in the argument of this cosine function will mean that the wave will propagate to the right. But here's how we'll begin to see that. So now what I do for the next moment in time is I set the time here equal to 1/4 of a period. So this is equal to 1/4 of 4 seconds, which is equal to 1 second. And now what I do is I go into the function and I set the time t equal to 1. When I set the time t equal to 1, then what I have right here is a minus pi over 2, which mathematically acts as a phase shift. So now I have the following. For cosine, first of all, pi over 4x, and then minus pi over 2 times 1 for just minus pi over 2. So in terms of a graph, what I have to do is take a cosine curve and shift it to the right by pi over 2 radians. Pi over 2 radians is 1/4 of a wavelength. This begins then the process of seeing a simple mathematical pattern that develops as the wave evolves with time. Okay, let's go ahead first of all, however, and graph this out. So what I have to start with is just a little cosine curve. Remember how I do this for kinematics of simple harmonic motion. I start off with a little shortcut graph that is like so. Okay, I'm going to be shifting this wave here to the right-hand side as I go. So then therefore I now have to figure out where pi over 2 radians is over here on the left-hand side. Pi over 2 radians is 1/4 of 2 pi. It's 1/4 of a wavelength. So that's very simply this point right here on the graph. So now what I have to do is take that point and shift it until it's to the right-hand side here on the axis. When I do, I'm taking the entire graph and I'm shifting it by pi over 2 radians to the right-hand side. That then gives me the following. So once again, y as a function of x. And now I start my graph with this point here on the axis. That is like so. Where right here is 8 meters once again, and then here's the amplitude position of 4 and -4. But where is the original green cosine curve that I started with? Well, it is now propagated to the right-hand side here on this graph, this distance right here. There is the original green cosine curve. So notice that in 1/4 of the period of time, this original green cosine curve has propagated to the right by 1/4 of a wavelength. That's the mathematical pattern. In addition to that, let's follow a simple harmonic oscillator in this process. For example, let's say that we take a look at this portion here of the spring. This portion of the spring has now oscillated from this point to this point here on this graph. It has gone through 1/4 of an oscillation, 1/4 of a period of time has elapsed. Once again, that's the simple mathematical pattern that gets picked up here in this process. Pause this lecture, by the way, at this point, and take a look at the screencast that I've posted for you in today's folder with respect to the kinematics of a simple periodic wave, where I mention that pattern once again. Okay, now that you've watched that screencast, let's just go ahead and continue this process of graphing to ultimately finish part B of the problem. Okay, I'm going to erase a few things here as I go. Okay, as I do go in this process, I don't need these shortcut graphs anymore once I've constructed the graphs, so then therefore I'm going to erase them as I go in the interest of trying to keep the board as uncluttered as possible. Okay, now let's take a look at the next moment in time. The next moment in time is going to be 1/2 the period. So then therefore I have here 1/2 of 4 seconds, which is 2 seconds. And now what I do is I go into the function and I set the time t equal to 2. When I set the time t equal to 2, the 2's here will cancel out, and then I'll be left with a minus pi. So I now have 4 cosine of pi over 4x minus pi in terms of meters. So in terms of a basic graph, what I have to do is take a cosine curve and shift it to the right by pi radians. Pi radians is 1/2 of a wavelength. So then therefore, in 1/2 the period, the wave has propagated now 1/2 a wavelength to the right-hand side. But here's how we show that. Okay, once again, I'll draw, first of all, a little shortcut. Start off with a cosine like so. Okay, we're going to be shifting it to the right. And then I have to figure out where pi radians is. So pi radians is this point right here. So if I shift that point onto the axis, I'm then shifting the cosine curve pi radians to the right-hand side. So now when I start my graph, I start with this point here. That then gives me the following. Okay, so first off, begin by drawing with this point here as your starting point, and just start off by drawing a full wavelength. So right here is a distance of 8 meters. Here and here are the amplitude positions of 4 and -4 respectively. However now, where is the original green cosine curve that I started with? Well, it is now here. Like so. So now notice that in 1/2 the period, the original green cosine curve that I started with has now propagated to the right-hand side by 1/2 of a wavelength. Take a look at the little oscillator that we're following in this process. Notice that the little oscillator has undergone 1/2 of an oscillation in 1/2 the period. Okay, here is the next graph. Let's now see what happens at 3/4 of the period. So at 3/4 of the period, this is 3/4 of 4 seconds, which is 3 seconds. And now what I do is I go into the function and I set the time t equal to 3. When I do, I have right here a -3 pi over 2. Like so, all in terms of meters. And now in terms of a basic graph, what I have to do is take a cosine curve and shift it to the right by 3 pi over 2 radians. That's 3/4 of a wavelength. So here's my little shortcut. I have to figure out where 3 pi over 2 radians is. That's this point right here. Shift it until it's on the axis. When I do, I'm shifting by 3 pi over 2 radians. So then therefore it's at this point here that I start my graph. So y and x. Start your graph at this point here and begin by just drawing out a full wavelength. So here's 8 meters and then 4 and -4 respectively for the amplitude. And then the original green cosine curve that I'm following has now propagated to here. Like so. If you look carefully here, you'll notice that the original green cosine curve that I started with has now propagated 3/4 of a wavelength to the right-hand side. That's in 3/4 of the period. The little oscillator that we're following has now oscillated back to here. It has undergone 3/4 of an oscillation. And now let's see what happens for the last graph. In order for us to see that, however, I'm going to tilt my phone so you can see the other board. I need a little bit more room. Okay, like so. Okay, and now we set the time t here equal to a full period, which is 4 seconds. So now we go into the function and we set the time t equal to 4. Okay, when you do, you obtain the following as your function. Okay, and then it's pi over 2, excuse me, times t. So pi over 2 times 4 is -2 pi. So in terms of a graph, what I have to do is take a cosine curve and shift it to the right by 2 pi radians. But when doing so, you're shifting by a full wavelength. So then therefore you just end up with another cosine curve. And that just looks like this. Okay, so I first of all just draw a cosine curve here. I just draw one full wavelength. So here's 8 meters. Here's 4 and -4 respectively. But then the original green cosine curve that I've been following in this process is now propagated to here. The oscillator that we're following in this process is now oscillated to its original position. So after a full period has gone by, the wave has now propagated a full wavelength to the right-hand side, and the individual oscillator itself has undergone a full oscillation. Now, of course, I went through this process here in part B of this problem very rigorously and very carefully. However, a problem like this is actually quite easy once you understand how the pattern works. For every quarter period of time, this then means that the wave propagates by 1/4 of a wavelength, and all the individual harmonic oscillators undergo 1/4 of an oscillation. Okay, let me retilt the phone back towards the main boards. Like so, and then lastly, let's take a look at part C of the problem. Okay, for part C of the problem, we're going to look at just a specific moment in time. That is right here at t = 1/2 the period. So then therefore, I don't need the remainder of the problem here for part C. Okay, and now specifically for part C, at this moment in time when the function looks like this and the graph looks like this, it says at 1/2 the period, where is y equal to -2 meters? This is all going to be calculated within the first wavelength here, by the way, on this graph. So right here is y equal to -2 meters. What we're asked to find is this position here and this position here of x, when the value of y is equal to -2 meters, all within just the first wavelength, and that's fine. So now what I have to do here is set the function itself equal to -2 and then just solve for x. Like so. So divide by 4 to the other side, take the inverse cosine of both sides of the expression like so. And now in radian mode on my calculator, I'll do the remainder here of the math. All right, so the left-hand side is the inverse cosine of -2/4. Okay, if you're checking at home, this is about 2.09 or so. Okay, and now I'll add pi to that, and then cross multiply by 4 and divide by pi. And after I do the math here, I end up with a value of x equal to about 6.67 meters, which is actually pretty obviously this point right here. Let's refer to this as x1. And then therefore, by symmetry, if I subtract the x1 from 8 meters, then I can pick up the second point here, x2. So x2 is going to be 8 minus 6.67, which is 1.33 meters, like so. And just calculating these values of x here within the first wavelength is perfectly fine. Okay, briefly, there will be a part 3 to this lecture. Here in parts 1 and 2 of this lecture, we were always starting the clock when you begin with a simple cosine curve, and then we just watch the propagation of the wave as time goes on. But of course, you could start the clock whenever you want. So how do you take that into account mathematically? Well, we'll get to that in part 3 of this lecture.